Alex, I'm going to lie to you because lesson 3 is called types of forces. And like much of what I'm teaching you, I'm actually teaching you wrong. For example, in our physics world in free fall, we ignored air resistance. We just pretended we were always falling in a vacuum because air resistance is yucky. Well, for types of forces, Rebecca, technically there's only 4 fundamental forces. There's gravity, there's the strong nuclear force, now just called the strong force, the weak nuclear force, now just called the weak force, and electromagnetism. And you can break everything down, everything comes down to those 4, but we don't want to always have to refer to everything in the, for those 4. So we're going to talk about some forces that are actually combinations of all of them. And we're just going to say they exist, even though technically they're really mythical, whatever. So types of forces, most of which don't exist. We will look at gravity. Gravity exists, but I'll be giving you some other ones that technically aren't real. A little thought experiment. The tension in the rope in the bottom case is greater than, B, the same as, C, less than the tension in the top case. You know what? Once again, this gives us a chance to vote. Once again, how high you hold your hand up is how sure you are of the answer. So we have a picture. We have 4 guys pulling on a rope where the rope is attached to a column. And then we have 8 guys pulling, 4 in either direction. Who says, Mr. Dewick, the bottom rope is feeling, was 8 people. It's got to feel more tension. No one. Who says, Mr. Dewick, it's the same as? Is that a hint? Yeah, okay. Who says less than? Okay. There's always one. Convince me. First of all, again, it's always, you can attack someone else's answer as being wrong, or you defend your answer as being right. So it's attack or defend. Convince me. Yeah.
The 8 people can exert a stronger force than the 4 people, because if they could, the entire system would accelerate.
It'd be wonderful if there was some kind of a law that I could refer to, one of 3 possible laws that I might want to fall back on. I would argue, first of all, this is Newton's 3rd, forces come in pairs, because if the biggest these guys can make is, let's say, 1,500 newtons, then the biggest that these guys can pull is 1,500 newtons, and it's not 3,000 newtons in the rope. The rope feels 1,500 newtons. Sorry, Trev. This is, I think you might have been here when I brought the scale up and I had 2 girls push, and then I said, who thinks they can do better? There's always some guy that says, oh, I can do better. But as long as I kept the girl that could only push with 150 newtons in the system, the guy could only push with 150 newtons. Or if you want to really make it more obvious, imagine we had a feather dangling from a piece of string, and the feather was just dangling there. Could you apply 10,000 newtons to the feather? No, because the feather can't apply 10,000 newtons back. Forces come in pairs. Is that all right? Okay. That was just to jog our memory after a long weekend. By the way, I'm impressed that so many of you went with B, because I know 2 weeks ago, and to non-physics people, even Mythbusters got caught in this one time. Jamie Heineman had to redo an entire... the myth was 2 semi-trucks were in a head-on collision. And then when they brought in the jaws of life and they separated the semi-trucks, they found a compact car smashed between them. So the myth was, could you crush a compact car between 2 semi-trucks? And Jamie said, oh, I'll just run 1 semi-truck twice as fast into a wall. That'll be the same physics. No, it's not. Anyways, and they had to redo it for a couple, well, probably $10,000 of cost. Ready? Gravity. Gravitational force. Symbol. Capital F for force with a little g. That's my symbol. There's another symbol that you'll sometimes see, and I'll show it to you in a second. What's the equation? Well, force, we did this last class, equals ma, but what symbol have we used for the acceleration due to gravity? G. So you know what? Fg equals mg. I'll use those interchangeably. Often, rather than writing Fg, I'll just put the mg in there right away because I know Hedrick it's going to show up. direction. Okay? Down, if you want to be really technical, towards the center of the planet. Because in Australia right now, their down is our, you know what, right? And in fact, you'll notice, Andy, without even realizing it, I left the vector symbol off here because the direction, it depends where on the Earth you're standing. But we can say it's always towards the planet's center. Does anybody remember another word for the force of gravity that we've used? Now. Weight is not mass. Weight is newtons, it's mg. And so sometimes you might see a capital W for weight. I know one of the handouts that I'm going to give you has that. I don't use it. I like to have, if it's a force, let's have an F and then a subscript, but that's how my brain works. So, Shelby the ballet dancer has a mass of 45 kilograms. What is Shelby's weight in newtons on the Earth's surface? Her weight is mg. It's going to be 45 times 9.8. I think I can do that in my head because it's going to be 45 times 10, which is 450. Take away 441? No? Yeah? Newtons. Given that 1 kilogram of mass corresponds to 2.2 pounds on the Earth's surface, what's Shelby's weight in pounds? Pounds is the imperial measure of the force of gravity. Well, we would go like this. 45 kilograms times, we want kilograms to cancel. What's the abbreviation for pounds? Why the heck LB? I have no idea. And so I have to handwrite it because I hate doing a lowercase l. Looks like a 1 to me too much. Anyways, or you know what? Actually, no. We started to get clever and replace it with the pound symbol. I'll take that one as well. That works, and there's less confusion. By the way, I have no idea where the LB comes from. What, again, stupid system. America, ditch your guns, go metric, for Pete's sakes. And I think the 2.2 is going to be on the top, yes? So first we would find her mass in kilograms, multiply. This goes straight to pounds. The 2.2 actually includes the unit of force. I can do that in my head as well. 99? Yes. 99 pounds. I don't think I'll ask you to do that again, but. What would Shelby's mass be on the surface of Jupiter? Jupiter doesn't have a surface, Connor. Okay, fine. If Jupiter had a surface, I know it's a gaseous planet, but if we had a planet the size and mass of Jupiter that had solid surface, what would Shelby's mass be on Jupiter? Too slow. What would Shelby's mass be on Jupiter? Too slow. What would Shelby's mass be on Jupiter? Mass. 45. Mass doesn't change anywhere in the universe. That's why I said too slow. What would Shelby's mass be on the sun, on the surface of the sun? I know, but if you could stand, what would Shelby's mass and survive? What would Shelby's mass be on the surface of the sun? 45 kilograms. In fact, what would Shelby's mass be in the middle of outer space? 45 kilograms, because mass is not the force. Mass is how much inertia you possess. It's really a measure of the total number of atoms in your body. What would Shelby's weight be on Jupiter, where the acceleration due to gravity is 25 meters per second squared? Fg, how about capital J for Jupiter? Would be m times gj for Jupiter. 45 times 25. I should be able to do that one in my head. It's going to be 1125? Yes? 1125 what? Units? Newtons. Okay? This is the difference on other planets. Courtney, on other planets, your mass doesn't change. What changes is how hard the planet pulls down on you. So on Jupiter, you would have an incredibly difficult time even lifting your head up, where on Mars, which has about a quarter of the Earth's gravitational field, you would feel 4 times lighter. Has your mass changed? No. What's changed? The force of gravity. Mass is unchanging and universal. Whatever your mass is, it's the same anywhere in the universe. Okay, I'll take that back. Weird stuff might happen as you enter the black hole because the atoms, general relativity, anyways. And let's assume you're not traveling near the speed of light. So let's add those once and for all. I'll mention that there are exceptions, and I'll say we're going to pretend that those aren't the case. Anywhere in the universe, Matt, your mass is unchanging. But the force of gravity, that depends on your location, where you are. Pause here and complete section A of the homework. I'm actually going to let you work on that later. I think I'm going to get about halfway through today's lesson, and then I'll let you work on this later. Suppose a 12,000 Newton truck is sitting at rest on the ground. Draw a free body diagram of the forces acting on it. Okay. What are the forces acting on the truck? Get the obvious one. In fact, I could even be really specific if I wanted to, since they told it to me in newtons. Convenient of it. Is the truck sinking into the ground like quicksand? Is it flying into the air like Superman? So what can you say from Newton's first law? There's another force? Which way? We're going to give this force a special name. Oh, and I know it's the same size, otherwise it'd be... We're going to give this force a special name in a second, but for now I'm going to say it's the ground. By the way, I don't want to use FG for ground, because FG is gravity, so I write out the word ground. It only got so many letters in the alphabet. Suppose we add a 2,500 Newton piano to the back of the truck. Okay. What are the forces acting on this truck? Get the obvious one. And I'm just going to label it with a 12,000. What else? What's changed in this question? Piano. Which way does the piano push on the truck? Down? I'll move it off to the side a little bit so that my arrows don't overlap. What else? Is this sinking into the ground like quicksand? Is it flying into the air like Superman? So there must be a force up, but how big is the force up going to be? If I go back here, this had to be 12,000 newtons. How big does this ground force up have to be here? More specific. As a number, how big? Otherwise, it would have to be sinking into the ground like quicksand if it was less than 14,500, or flying into the air like Superman if it was more than 14,500. So Megan, what I want you to realize is the ground, truthfully, it pushes up as hard as it needs to, or as hard as it can, because if this was quicksand, the reason quicksand is it can't push up very hard. Right? It's not the quicksand. By the way, people say quicksand sucks you down. No. What force is sucking you down into quicksand? Gravity. The problem is quicksand can't match the force of gravity. Okay, but it's not quicksand sucking you down. It's gravity. This force, Alicia, of the ground, or any surface, like the chair that you're sitting on, like the table that your book is resting on, any surface pushing up to prevent the object from sinking has a special name. We call it the normal force. Symbol Fn. Years ago, I was marking provincial exams, and there was a question that said this. And the student wrote, which was funny, but they still got a 0 on the question, so just, okay. I mean, at least they knew that they could have a sense of humor. On those grade 12 provincial exams, you saw some crazy stuff, because a lot of the times kids were writing them knowing they had no chance of passing the course, and it was like June 26th when they were writing them, so they were going loopy, you know, they had full-blown graduitis, and so you get all sorts of clever stuff. But anyways, don't do that on a test, please. The normal force. This is a This is a forces come in pairs force. It's a reactive force, if you want to call it that way. The result of Newton's law, which was forces come in pairs. Because of that, because it's only reacting, it's matching the force, it's only, Alex, as big as it needs to be. Beyond a certain point. Eventually it can't get any bigger, and then the ground will cave in. That's what a jackhammer does, for that matter. Okay, so you can't apply a bigger force than the ground can put out, but otherwise it's only as big as it needs to be. It's the force that the ground pushes back up us to satisfy Newton's first law, because none of us are sinking into the ground like quicksand or flying into the air like Superman. How big is the normal force in the following situations? Okay. What are the forces acting on this mass? Get the obvious one. Is it sinking into the ground like quicksand? You know what? Let's crunch it. What is mg? What is 5 times 9.8? More specific. It's not 49. Can you be more accurate, please? I don't think 5 is 5 times 9.8. Is it 49? Is it 49 even? Oh, it is. I'm sorry. You're right. I was forgetting to carry a 1. Good gosh. 49 newtons. Is this mass sinking into the ground like quicksand? Is it flying into like Superman? No. So how big is the normal force now? Now I'm going to label it with F. My symbol for normal force is that, and it has to be okay. In fact, the phrase you'll hear me say is, I don't know the normal force. Oh, but look. I know another force the same size as the normal force, mg. B. How big is the normal force? I don't know the normal force. Oh, but look. I know several forces that can help me figure out the normal force. So I have mg, which is 49 newtons, and then apparently someone else is also pushing down with an extra, how many newtons? 30. How big must the ground be pushing up at then? In your head, please. 79, I would draw the normal force much bigger than mg. In fact, I'd try and draw it roughly as long as both those arrows combined, and I would say the normal force equals 79 newtons. I have, Alex, no equation for the normal force. In fact, there might be one. I don't know it. It's always draw a free body diagram and then use Newton's first law to figure out how big the normal force has to be. Here we have, again, mg equals 49 newtons. Is this mass sinking into the ground like quicksand? No. Is it flying into the air like Superman? No. How big is the force up? Not 49. 37. Someone else must be tugging up, and the ground then doesn't have to push as hard. And this brings us to a question. What does a scale measure? Let me pause the video for a second. Have I convinced you? Is that okay? Scale can't measure mass. Scale can't measure weight. A scale does not measure mass or weight. A scale measures FN. Now, why is that going to be important? Because Lindsay, in a bunch of questions in the homework, I'm going to be asking you to tell me what a scale is reading. Which force am I really asking you to find, Lindsay? Normal force. Okay? Normal force. So when I ask you to find what a scale reads, that's what that young man on the provincial exam didn't realize on that particular question. Because when it said find the normal force, the question did have a scale in it. And if he showed, oh, find the force on the scale. All of you right now feel a normal force of mg. A good amusement park ride just mucks around with the normal force. How hard your chair pushes up against you. Because they sure as heck can't change your mass. And they sure as heck can't change gravity. But changing the normal force, oh, that's good stuff. Put your pencils down, look up. So this brings us to the famous elevator question. Now, if you want to, just to exaggerate things, Courtney, you can think, instead of the elevator, think a helevator, like the ride at Playland. So when it says accelerating up, because it's more noticeable then, and when it says accelerating down, it's more noticeable then. But here's what it says. 72-kilogram man stands on a Newton scale in an elevator. So this is a scale that reads in newtons, not in kilograms. What does the scale read if the elevator is... Now, what am I asking you to find here? What does the... First of all, Lydia, what does the... What am I really asking you to find here? Normal force. Okay? What does the scale read if the elevator is accelerating upwards at 3.2 meters per second squared? This is a job for a free body diagram. Right here. What are the forces acting on this person in the elevator or the person on the ride on the helevator? Get the obvious one. Quickly, money. Sorry? Gravity down. Matt, what direction is this person accelerating according to part A? What direction must the winning arrow, bigger arrow force be according to part A? What force? The normal force, your chair. I'll exaggerate it like that. Now we're going to use our tug-of-war approach. Remember our tug-of-war? We asked, who's winning? Alex, who is winning? Loud and proud, with authority in your voice. This is why, by the way, I'm so intense about drawing the diagram, because now it becomes obvious. Who's winning? Who's the loser? And what does it always equal? Do you remember? MA. Lydia, what did you say this question was asking me to find?
No, sorry.
The scale, but what was it really asking me to find? Normal force. See it? How would I get the Fn by itself? How would I get the Fn by itself? Yeah? Yes. Fact. You ready, Matt? On the way up, this is the physics. So now I can answer the question that I posed during the roller coaster video. Don't write this down, just look up. This is what you normally feel. All of you right now are feeling mg. On the way up, are you going to feel heavier or lighter? Why must you feel heavier? Because we're adding something. Oh, and the more we accelerate you up, the bigger A gets, the heavier you'll feel. If you've been on the who's been on the elevator? So next, if you're on it again, next time you're on it, concentrate on the sensation. On the way up, that stomach moving down feeling, that's really your body feeling an increased normal force. That one's not as bad. We don't mind feeling heavier because you feel that whenever you piggyback someone. Really? Yeah. Your feet feel a stronger normal force. You feel it whenever somebody dog piles on you. All of you have had the experience of having extra mass on top of you. What freaks us out, more than on the way up, on the way down, because that's when you swear you're going to fly off the seat, right? You're not, but we don't, there's nothing in your normal experience that gives you a lighter normal force. Swing sets, by the way, you get a heavier normal force on the bottom. You've all experienced the feeling of being heavier, and when you were a kid on the playground, you liked it. Hey, let's crunch the numbers. Matt, what was M? Yeah. 72. What's G? 9.8 plus, not negative. We took care of the negative with that arrow pointing down. What's M again? 72. What's A? 3.2. What will the scale read? Or what would your rear end feel if you were sitting on the elevator through the chair? You'd feel heavier. It's just a little awkward to say, what does your butt feel? So we'll pretend you're sitting on a scale, and that gives me something clinical to ask you. You get 936? Yeah. Units, it's a force. Newtons. Is that okay, Court? I'm going to skip B. Let's go to C. By the way, B is going to be very, very similar to A. You might be tempted to just use the same equation, but I would say I would draw the free body diagram. Let's go to C. Let's go to C. Alicia, how is C different? Which way are we accelerating? But it still wants me to find what the scale reads. Which force is it really asking me to find? Normal force? This is a job for a free body diagram. What are the forces acting on this person? Get the obvious one. Yep. What direction is this person accelerating, Alicia? So who's winning? Yeah. So there is going to, by the way, are they accelerating at 9.8? Say no. So there must be a force up, because if they were in free fall, it'd be 9.8. Yes? So there must be a force up, bigger, smaller, or the same size as gravity. Who did you say was winning? So there's going to be a normal force, smaller. That's what the little kid experienced, by the way, going down the hill. And that's something that we're not used to. So can I, are you okay, Alicia? I'm going to do that. Really exaggerate it. Who's winning? Who's losing? What's my equation going to be? What minus what? Equals what, always? MA. What did you say we were trying to find? Let's get the Fn by itself. How would I do that? We've seen this dance before. What's right in front of the Fn that I don't like? Do you mind? I'm going to plus it to that side. At the same time, I'm going to minus the MA over, because the MA is positive. So I'll minus it. Is that okay? And I'm going to get this. mg minus MA. And I'm also, Alicia, going to put the normal force on that side. Is that okay? Put your pencils down, look up. Right now, all of you are feeling that. But when you accelerate downwards, do you feel lighter or heavier? Why lighter? Because we're subtracting something. And that's the one that really gets our attention. And I think that's built into us because that means the branch is breaking back when we were in trees. I think it's wired into our lizard brain from way back when. Swings we love because in a swing you feel heavier. I haven't seen too many playground rides where you feel lighter. We don't seem to like that as much. Just a little trivia there. Oh, plug and chug. What's the mass, Alicia? The mass? Yeah, you do. Go read your question. It's in the description. What's the mass? The mass, that's an acceleration. Mass, what's mass measured in? Go look in the top part of the question. It's in the description, kiddo. Yes, why? Because what's mass measured in? Kilograms. Okay, ready? Here we go. What's the mass, kiddo? Good. What's G? Yep. Do we need to put the negative in? No, we took care of that with the arrow. Yes. Minus, what's the mass? What's A? No. Yes. Folks, can you crunch that? What do you get for the normal force? Sorry? When I say sorry and you say the same volume, it doesn't help at all. Louder? 331.2? Is that what you said? 331.2? Units, Alicia, it's a force. Newtons. Now, here's the problem, just for what it's worth, Haley. Scales don't read in newtons. What units do scales use? Kilograms. How would you change newtons to kilograms? Because that's what part B said, right? Part B says, what would the scale read in kilograms? How do you go from newtons to kilograms? It's really easy. You divide by 9.8. That's all the scale is calibrated to find the normal force divided by 9.8. So if we call this part A, part B, if you go 331.2 divide by 9.8, you can make a little note here. Divide the normal force by 9.8. Or if they give you a normal force in kilograms, times it by 9.8 to actually make it a normal force. What do you get? Sorry? 33.8? Is that right, folks? So if this person was sitting or standing on a scale in an elevator and they looked down, it would look like their mass was 33.8 kilograms. Is their mass actually that? No. The normal force is 33.8 times 9.8. Is that all right? We're going to skip D. Let's do E. What does E want me to find? The scale reading. What does it really want me to find, Courtney? When I say scale reading, what am I really asking you to find? Nice and loud and proud, people. Okay. This is a job for a free body diagram. What are the forces acting on this person, Courtney? Get the obvious one. I like that. What else? Who's winning? Well, which way is this person moving? Let's assume downwards is the winner. So let's draw a short little normal force up. Is that okay? Who's winning? Who's losing? You with me so far? What does that always equal? Okay. By the way, what's the key phrase in this question that this time I didn't point out because I wanted to see if you guys would spot it? Yeah? All of you right now might want to underline that. Because what does constant velocity mean? As a number, what's the acceleration? That no acceleration drives me crazy. A is 0. Courtney, what's 5 times 0? What's 10 times 0? What's m times 0? So if I hear you correctly, and I think I do, you're telling me this. Yeah. Oh, how would I get the normal force by itself? Add the mg to the other side? I don't know. What are we trying to find? What are we trying to find? Okay, so we want to get the Fn by itself. What's right in front of the Fn? How could I take care of that minus? What's the opposite of minus Fn? Okay, so you're saying I could plus it to this side like that? Courtney, what's 0 plus 10? What's 0 plus a million? What's 0 plus Fn? Are you saying that really I can just go like this? Okay, what is mg, folks? Oh, Courtney, what was the mass? Was it I've forgotten. 72? What was g? 9.8? It's going to be 720 take away 14.4. 705.6? Yeah? Newtons, because it's a force. Newtons, because it's a force. Okay? Again, Ryan, lots of power in a free body diagram. We're going to finish here with F, and then we're going to pause. And again, Haley, I'm going to say, resist the temptation to try and memorize what the equation looks like when you're accelerating up, what the equation looks like when you're accelerating, because I can just stick an extra force in there and change the whole situation. What I am going to say is, you know what? Learn how to do a good free body diagram, and we're happy campers. So, Haley, accelerating downwards at 9.8 meters per second squared in free fall. What do you think a scale would read? Connor, prove it. This is a job for a free body diagram. I can prove this. What are the forces acting on this person, Connor, my friend? Get the obvious one. Uh-huh. Is there a normal force? I'm not sure, but I know one thing. Gravity's winning. So, you know what? I'll put it there just in case. I'll hedge my bet. Who's winning? Who's losing? And that always equals ma. What are you trying to get by itself? Oh, you know what? I can plus it there, and at the same time, I can minus it there. You okay with that, Court? That, by the way, that trick of making the thing that you want positive by moving it to the other side and getting on the other side back to this, we're going to use that an awful lot. And if you can wrap your brain around that, doing it in your head, Trevor, I say, please do. Is that okay? So, Connor, I think I'm going to get this. The mg drops down like a domino, yes? Minus ma, that equals Fn. All right, let's plug in chug. What's the mass? Put your calculator down. What's the mass? What's G? Minus, what's the mass? What's A? Without a calculator, in your head, showing no work, what would 72 times 9.8 take away 72 times 9.8 be? What's the normal force when you're in free fall? What would the scale read? What would you feel your weight was? 0. Are you weightless? No. Gravity's still there. We call this apparent weightlessness. When I jumped out of an airplane, I felt weightless. I wasn't, but I felt it. This we'll also enjoy, but not all of us. Some of you are comfortable jumping off the high dive. Some of you are not. But that split second while you're in the air, coming off the high dive into the pool, you're weightless. You're weightless when you're jumping on a trampoline while you're in the air. But you're apparently weightless. You're feeling no normal force. So let's finish off. So you were right, but there's a lovely proof. Now, you can file that in your brain, and I won't make you prove that again if I ask you on a test. If you're in free fall, what does a scale read? But for what it's worth, hopefully I've convinced you. Okay? We are going to you can do all of section A, and then you can do section B number 1, number 2, number 3, number 4, You can try number 10. We're going to finish this and do the rest of the questions later, but if you want to try number 10, number 11, number 12, 13, 14. Ryan, looking at number 13, what is number 13 asking me to find? What force? I think you can just go F equals ma. They didn't give me the acceleration. I bet you can find A using the stuff from before Christmas. Vf equals Vi plus At, Vf squared equals Vi squared plus 2Ad, D equals Vit plus a half At. Those are all back in play. Okay. Then we'll finish this lesson off with looking at air resistance next class. If you don't get all the homework done, you'll have some time on Thursday as well. And on Thursday, you'll also work on the take-home quiz. Although if you've wrapped your brain around elevator questions, you can start the take-home quiz now. I showed you both parts of the video, why inertia, why the Earth spins. Yes, I think I did. Part 1 and Part 2. So